So first of all, I'd probably want to just think about what the current's actually going to be like. So we've got a DC supply, put time on this one, current up there. So when the circuit's open, the switch is open, obviously there isn't any current, then you get this point, turn the switch on and you'll see the current will build up very quickly, become constant, open the switch and back down it goes. So we've got two places really, or 2 points in time when the current's going to change pretty quickly. In order to explain how Lenz's law predicts the current and direction of the induced current, that is in coil Y of course, we have to think about what's going on in coil X. So I'd say, first of all, write out Lenz's law. I tell my students to learn this as a definition. Lenz's law says the direction of the induced current acts to oppose the change that created it. And of course, to get the marks, you've now got to go on and explain that. So let's walk this through step by step. So the first thing we're going to say is that you close the switch. So when you close the switch, that means there's a rapid increase, I can't spell, you'll learn that, a rapid increase in I in coil X, right? So this, that creates a rapidly changing flux in X. So let's just illustrate that. So as soon as you close the switch, very quickly these field lines will develop through the first of the coils there, like this. Now, obviously there's nothing there before, and we don't know which direction these field lines are in. Well, it doesn't matter. It really doesn't matter. But all what matters is that we are building up quickly and rapidly a changing flux in coil X there. So that means that Y is sitting in a rapidly changing flux, and therefore in Y we're going to induce a current. So a current is induced in coil Y. I always say it's a good job I'm not an English teacher because of my rubbish typing, but you know, you get the idea. Induced. So we're going to have a significant current then being induced in coil Y. Now whenever we have a current, we always, by definition, have a magnetic field. So that magnetic field that is induced, sorry, I should say that current that is induced in Y is going to in turn create a magnetic field of the same shape, because it's the same shape coil, out of Y. I mean, probably should write that. So current is induced in coil Y, creating a magnetic field from Y. And the question is which way are these flux lines going? Well, Lenz's law tells us that they have to oppose the change that created them. So therefore they're going the opposite way. Now we know that in order to create field lines going the opposite way, current also has to be going the opposite way. Therefore, the current in coil Y must be going in the opposite direction to what it is in X. Let's write some of that down. So something like this. So the current in coil Y must be in the opposite direction to that in X in order to oppose the change that created it. Remember, that's to get the flux lines, the red ones, to be going in the opposite direction. A slightly different way to think about this is that when you close the switch, the flux lines in X are building up. Therefore, the flux lines in Y will act to decrease that build. And this is helpful when we're thinking about what happens when we open the switch. Well, when we open the switch, the flux lines in X decrease rapidly. So open switch, flux decreases. Rapidly. This means that the flux lines in Y must be the other way round, going from left to right, because they have to act to oppose the change that created them, and the change that created them is a decrease in flux. So they have to flip over the other way to try and build the flux back up. So open the switch, flux decreases rapidly, I suppose we should say, from X. Therefore, Y has to oppose this reduction, and so the field lines swap direction, i.e. the current becomes clockwise. And that's that. That's a complicated question, but I love it.